My name is Eric. I'm going to talk a little bit about some more advanced methods in Markov chain Monte Carlo. It's really building off some of the things that Bob just discussed. So before I want to start, I want to make two important parts. First of all, I'm going to focus on the big picture of the algorithms rather than the specific details in the implementation. So if you want these details, if you go to the Flam2 website, all these slides will be up there, and I have a reasonably extensive annotated bibliography at the ends of the slides. So you can go there and go to those references and actually find the precise implementation details. And of course, I'm always happy to talk about them myself. So I want to recap a little bit of Markov chain Monte Carlo, just for people who might be a little new to this. And the basic problem that we run into with Markov chain Monte Carlo is often we want to calculate an average against the density. And for most of this talk, I'm going to assume that the density is known up to a normalization constant. But the integrals against this density are too high dimensional or otherwise intractable. So for instance, here, we had a question last time about the evidence. The evidence is the denominator here. And unfortunately, for most complex Bayesian models, we can't evaluate this directly. So we instead would only be able to evaluate expectations up to a normalization constant. So what does this look like in Bayesian MCMC? Well, there, this P of X is really a P of theta. It's a probability of our parameters. And this is exactly the posterior probability that we see a given parameter. Excuse me, this should be rho of theta. And then P of theta here is our prior, of course. And this integral in the denominator is the evidence. In statistical mechanics, which is the community I come from, rho of X is the Boltzmann weight. And then the bottom is the partition function. So the way that we solve this problem, Markov chain Monte Carlo, is we construct a Markov chain that is stationary and ergodic against rho. And what this basically means is that averages over this chain, which is sort of this repeated, this stochastic process where I just perform a sequence of jumps from point to point, that converge to averages over this rho, which ended up floating a little bit, excuse me. And basically here, right, I take my trajectory from xi starting 1 all the way to n. I average over my trajectory, and for enough samples, this is going to converge against my average against the density I want. You can sort of visualize this here, where if maybe for like 100 samples, then the yellow is the density, and it is like a density estimate of what I've actually sampled. As I keep adding the number of samples, the density of my samples more or less converges to the density that I'm trying to approximate the blue density. So what does this look like in practice? Again, this is a recap for many of you, but I'm just going to give a quick recap of one of the most basic Markov chain Monte Carlo methods, the Metropolis-Hastings algorithm. So for Metropolis-Hastings, basically once we're at a point xi, we draw a proposal for the next point in the chain, yi plus 1. And then we basically accept the proposal with a probability which is 1 if this let point is more likely than xi. And if it's not more likely, we have this ratio over here, which is a combination of the probability of us proposing that point as well as the probability of that point from rho. And then if it's accepted, then we move to that point. Else, our next point is just the same point we're at. So this sort of introduces the notion of a proposal density, Q, and also these sort of acceptance probabilities. And in practice, you're likely to use a more complicated method like Hamiltonian MC or no U-turn, which is what really drives STAM, or inertial Langevin, which is what really drives much of the MD community. But this sort of intuition of I'm going to have a proposal and then I'm going to accept that with some metropolization, some probability here is really sort of what underlies a lot of these methods. Now, over here, I talked about the fact that this average will converge, but there's a good question of how can we check if that average actually converges? In practice, when we run these chains, a lot of the times, sure, if n is large enough, it'll converge, but we might need more simulation time than we might need years of simulation time. Some projects, maybe if it's bad enough, if we just naively run a basic Markov chain, it might take longer than like the age of the solar system to converge. And how can we, if we have bad convergence problems, how can we diagnose them and how can we improve them? So I think the first thing you should always do is visual inspection before you do anything fancy. So here I have two chains, and you could sort of ask, like, which of these chains converged? So on the left, you see this sort of phenomenon, which is like this warm-up period that often happens when you start running these chains, right? That initially you might initialize them poorly, but then you'll relax to the correct mode, and then you're actually going to get some oscillation around that mode. But then you get reasonable sampling. So I'd say after this point, after this, what's called the burn-in, or like the warm-up in STAM, then you actually have a converged chain. On the right other hand, you have a chain that has a little bit worse convergence properties. You notice there's sort of difference in behavior between the first half and the second half. And sure, maybe, and you notice that even if you look at how many times I'm really seeing fluctuations over my coordinates, I'm maybe getting like not many samples. So this is like a rather, so you're just looking at the time trace, you can already tell a little bit about how converged the chain is. And this is definitely the first thing you should always do. But we can actually be a little fancier. One thing we can do is we can run chains, identical chains, with a different initial points. And there's a statistic, the R hat statistic. And the basic idea is if my chain is converged, I run multiple chains from the same location, they'll all have the same statistics. And contrast, if I have chains that aren't converging well, then each chain, then the statistics within the chains will not match the ensemble. And what the R hat statistic does, and the formula is a bit complicated, but so I'm not going to put it here, is it compares the variance of each inside each chain to the variance of the ensemble of chains. So if the chain is perfectly converged, then the R hat statistic has a value of 1. However, if you're poorly converged, it's going to be much greater than 1. And a good threshold that I think is recommended by STAM, Bob can correct me if I'm wrong on this, is that you probably want it to be around 1.01 or less to be really confident that your chain is converged. So this sort of gives a bit of a qualitative measure. I mean, this is a statistic, but ultimately it's not really telling you about like the actual variance of your simulation, and a quantitative measure of the number of samples, how converged you are. So what you really want to quantitatively assess convergence is something like the autocorrelation time, or also known as or equivalently the effective sample size. Idea with the effective sample size is if you just think about just a naive average with independent samples, I know how the variance of that average converges. It converges as the variance of the function divided by the number of samples. However, in Markov chain Monte Carlo, I don't have independent samples. I have samples that are correlated with each other. So instead, I need this additional multiplicative factor, the autocorrelation time. And this is really, you can think of this as an exchange rate. The autocorrelation time says how many samples of Markov chain Monte Carlo I need to trade in to get the same statistical power as one new independent sample. And often this is given in terms of the effective sample size, so n over tau. And then having an effective sample size of greater than 100 is probably reasonable, is a reasonable start to be confident in your model. Although, of course, this is very application dependent. A little bit about the intuition of this sort of intuition that if you actually like look at the time trace, tau is about the time you can see for these, in this case, these oscillations to occur. To be able, you want to take these sorts of back of the envelope estimates with a grain of salt. It depends a little bit on your sampler. If you have something that really sloshes back and forth, maybe this is not such a good way of assessing tau. But here, for instance, for protein simulation, when they have very Brownian-like dynamics, then basically these sorts of, you can sort of eyeball tau a little bit. I can also calculate it effectively by integrating under the correlation function. So here what I've done is the formal definition of tau is as follows. I take the function, I subtract the mean, and then I calculate the autocorrelation for the mean zero version of this function and integrate it. Then this correlation function will decay to zero after the chain is decorrelated. So the terms after that point will contribute almost nothing to the sum. Now, while this definition looks nice in practice, it's actually hard to compute this sum accurately, because just naively summing this all the way to as long as you can, if you do that, the variance of that estimator will actually explode. So it's a bit of an area of active research how to calculate this accurately, and it's a hard problem. But there are good estimators that are implemented in Stan as ESS, or if you're using MC, there's an autocore subpackage that will estimate tau for you. So I would recommend using those estimators first. And of course, always look at the autocorrelation function yourself. So this is an example I got a few weeks back where we had a very poorly converged chain. And if you think about the autocorrelation function, it should decay to zero. But if you look at this, I think it's pretty clear that this Markov chain is probably not converged. So we've talked a little bit about like how you can tell if your Markov chain isn't converging, but you could also ask the question, why is it not converging? And two of the common bad culprits, apart from just like bad parameter choice by the user, is bad scaling in the problem and a multimodal probability distribution. So bad scaling happens when the Markov chain Monte Carlo moves you have don't match the actual level sets of your probability distribution. So here's an example actually from the Stan tutorials where I have this sort of funnel density where most of the density is sort of on this like little spike down here. So if I just run like a Metropolis Hastings sampler here, I spend most of my time bouncing here. But I actually have to get into the spike, which is extremely difficult because it has basically Lebesgue measure almost zero. So you're not really going to sample a lot of the distribution. So the first thing you should do is think about the way you've parameterized your model. Maybe, for instance, if you have a variable in there, but actually you expect normal variation in that model on a log scale, not on a linear scale, then you should probably have the log of that parameter as your input to your model. And similarly, if you have access to the Hessian of your model, you should consider rescaling your problem so that the Hessian around your max likelihood mode or around your minima is close to the identity. And of course, if you can explicitly evaluate the Hessian, this is great. And tools such as the Stan, I think, will allow you to actually plug in your second derivatives and use this information automatically. And then, of course, one thing you can do, as Bob mentioned, is you can take your warm-up runs, often from multiple things, and you can use this to sort of bootstrap an estimate of your covariance and what the scaling of your problem is. And I understand this is automatic in Stan. And Bob actually mentioned this when he gave like the 4 steps that goes on in the Stan sampler. So one area of research is actually trying to bake in resilience against these bad scaling directly in the Markov chain. So one of the first examples of this was the affine invariant sampler. And this is actually, if you go and run MC, this is sort of what MC is famous for, is having good implementation of this. It's a nice sampler. It has some advantages, which is one is it doesn't need derivative information, which makes it easier to use on black box models. So the way this basically, the affine invariant sampler works is I take a candidate, I lay down multiple copies, multiple little walkers on my probability space. And the way I make moves is I choose 2 of them. I choose one that's a candidate, and then I choose this green one, which I'm going to call the reference. And then I propose moves by moving along the line that moves between the candidate and the reference. And you'll notice if I stretch the space linearly, then because of the line stretches exactly the same way. And so my proposal distribution is going to change accordingly. So the property this ensures is that the Markov chain Monte Carlo scheme is unchanged if I stretch or translate my parameter space. linearly. If I'm performing a nonlinear transformation to the parameters, though, then that will make a difference. Now I'm going to talk about multimodality a little bit. This is the other problem. In multimodality, the issue I have is that if my probability distribution I'm sampling has many high likelihood regions separated by low likelihood regions, low probability regions, then it's very easy for me to get trapped in one of the high probability regions, because to pass out of it, well, by definition, I have to go through a low probability region. And this is rather hard to solve by changing only the proposal density, although I'm going to talk a little bit about one method to do that, replicate exchange. And I think the common approach to this is usually using some form of changing the probability distribution itself. And using probability distributions that are easier to sample, and then backing back out averages against your original distribution. And I also want to point out that a similar problem occurs when you're sampling tail probabilities. Because if you have a tail probability and you really want to nail down, then by definition, it's a low probability event, and you have the same sort of issue. For multimodality, you have to cross the low probability events. For tail probabilities, you actually want to be in there. But you still, the same sort of methods work in both cases. So I want to give a quick side note for the Bayesians in the audience. So recall just a bit about what we're actually doing in Bayesian statistics, right? We sample this probability of P of the rho of theta, which is the sort of like, it's proportional to the probability that you have a certain parameter set given your data. And there is sort of a bit of a folk wisdom here, which is I think it's encapsulated by the folk theorem of computing by Andrew Gell-Mann, which is that, but basically in this context boils down to, if the family of models you're using contains the right model, then you should reasonably expect to see like one good peak for the real parameters. So if you're seeing multimodality, it's often, one reason this could be is because you didn't choose a good family of models, and you're kind of trapped between sort of comparably bad solutions. So so it's not always true, but one thing is that multimodality can be a sign that you didn't specify your model correctly. Now, for physical systems, it doesn't make as much sense, because many physical systems, we know they're multimodal. If you have like an Ising model, right, you have at low temperature, you have two options. All your spins are south, all your spins are north. We know there's two modes in here. We can't get around that. But I think for the Bayesian for Bayesian settings, then sometimes this is something to take into account. Also, Bob, thanks for all the supporting comments in the chat. It's really great. So then I think one of the earliest approaches to addressing this is importance sampling. And the idea behind importance sampling is, okay, our old density is hard to sample. So we're just going to throw down a new density that is easier to sample, but sort of covers the same space. And this is what and this new density we're going to call pi. Now going back to our average, what we can do is we can then just multiply and divide by pi, and then fold this ratio of rho over pi into the average we're actually calculating. And then we sample pi, and then we just calculate this new average, and that will converge. Now, you have to be a little careful here, because if you choose this estimator badly, the variance can be infinite. And this is sort of a fun exercise for yourself. You sit down, write down the importance sampling problem between two Gaussians. And you'll notice if you take the sampling density, the importance sampling density, too narrow, once you hit a certain threshold, the variance of the denominator is literally infinity. And that is never a good thing. That's never a good thing to be happening. So how can you address this? And so one strategy that's pretty commonly used in molecular dynamics is you say, okay, fine, I might have trouble choosing one distribution that's bad, but maybe I can reweight using many states. And this has sort of been like reinvented in multiple contexts. This is very much related to extended bridge sampling, and also to, I found out yesterday, multiple importance sampling, which is a thing that's apparently used in computer vision for light refraction. But the basic idea is I'm going to introduce several bias functions, psi j. And then I'm going to sample these bias distributions, where I just multiply my old density by psi j, and I'm going to renormalize appropriately. And this really gives me a lot of flexibility in what I can do. So one thing I can do is I can just choose these psi's to be overlapping indicators on my original distribution. And once I do this, then I've sort of like chunked my old distribution into several chunks. And each of these chunks are reasonably easy to sample because they're all like reasonably unimodal, and the probability, the difference in the probabilities is not as big. Then I now have this, I've introduced all these like n new normalization constants I have to calculate, but there's actually, it's reasonably possible to evaluate these guys using the overlapping information between my state psi j. Now, this is a little, it's not this, and like many, I want to make clear, this, like many approaches for multimodal sampling, require you to have a little bit of understanding about what the shape of the distribution is and where the modes are. There's very few things that sort of work out of the box. There's kind of this like no free lunch thing that goes on, right? You have to have some information to be able to address these problems. So here, for instance, you kind of need, if you're going to do this sort of chunking procedure, you need to know more or less what direction you need to go in to encounter the multiple modes. So another approach is replica exchange. And the idea behind replica exchange is like, well, on my last slide, I sort of did the spatial chunking, but nothing really required that these biases like enforce spatial chunks. So one thing I could do is I could just take powers of my original density from some beta between 0 and 1. And the effect this has is that it flattens out my probability distributions. You see that these are getting like slowly, like more gentle. Now, this beta 3 distribution, for instance, is pretty easy to sample. But one of the issues is that if I wanted to, so beta 3 is nice, but it didn't really solve any problem with beta 1 equals 1, right? This is still just the same old hard to sample distribution. But what I can do is I can sort of use these new distributions as a route to jump between the modes of beta 1. And the idea is I'm going to start a chain in beta 1. I'm going to define a swapping procedure where I swap the chain in beta 1 and beta 3. I'll let it move through beta 3. And then I'm going to swap back to beta 1. And this is sort of visualized here. Beta 3 equals 0.1. What did I write? Yes, Bob is absolutely right. Beta 3 equals 0.1, not 1. So so this is sort of what it looks like. And so often here, this is parameterized by another variable called t in molecular dynamics. But then I sort of periodically attempt exchanges between my various different states, and I accept and reject them using a separate rule. And then if I do this correctly, the marginal in each state is exactly is pi j. So the marginal in the beta 1 simulation is exactly my original density, and so on and so forth. And people often just take that marginal for their sampler. But one thing you really should do is you should really use the same reweighting procedures from over here and really use all your data when you're doing replica exchange.
Eric, sorry to interrupt. So you're at the 25-minute mark, and it'll be good to have a couple of minutes for questions at the end. So just to let you know, this is
Absolutely.
reality.
Yes, Mary Lou. Yeah, and also Mary Lou asked if parallel tempering is another name for replica exchange. Yes, they're the same thing. So one other thing I just want to, in the interest of time, I'm going to mention really quickly about what to do if you don't know the density. So this is often a case we find ourselves in physical simulations, where the distribution is only implicitly defined as the output of a simulation, or maybe as some unknown stationary distribution of a Markov chain that is handed to us. And one thing you can do there is these approaches like sequential Monte Carlo. And there what we do is we rather than explicitly changing the Markov chain or explicitly enforcing a bias, what you do is you run swarms according to whatever sampler you have. but then you split and you kill the chains to move your chains towards good regions that you are estimating. So with that said, that's where I want to stay off. Big problems in Markov chain Monte Carlo. You have bad scaling multimodality. For bad scaling, you should really consider reparameterizing the system. But there are also approaches based on the Hessian and ensemble methods, a lot of which is like automatically implemented in Stan and MC for you. For multimodality, often you have to think a little bit harder. And approaches like importance sampling, umbrella sampling, and replica exchange, among others, will really benefit you. And then, of course, if the density is unknown, you got to split and kill trajectories. Yeah, with that, I'll end.